Swayam Prabha. Digital India. Educated India.
This is the first lecture of this course on chemical engineering thermodynamics. I thought I would give you an overview of thermodynamics in the chemical industry, the outline of this lecture, and I am going to use PowerPoint only for this lecture. And the outline of this lecture is as follows. I talk about the chemical industry in general, then I tell you a bit about thermodynamics, then I am going to tell you about the masters and their ideas, that is the people who actually developed the subject of thermodynamics. Tell you about the important aspects of chemical engineering thermodynamics that we will discuss, mainly work and equilibrium. In particular, I will talk about work of separation and show you that thermodynamics actually predicts market prices reasonably well. And then we will discuss a bit of reaction equilibria, and finally I will close with a molecular picture of mixing. I must say that classical thermodynamics does not depend upon the molecular structure of matter, and it is actually independent of that, but the molecular picture helps give you a handle on understanding what the properties mean in molecular terms. So, I will start off by telling you something about the chemical industry. The first thing that strikes you about the world of chemicals is you think there are infinite chemicals, but basically there are 4 groups. They are classified into 4 groups, and the raw materials that we discuss are usually oil, natural gas, coal, biomass, rock salt, sulfur, air and water, and the major fuels are LPG, gasoline, diesel, kerosene. The bulk chemicals are divided into base chemicals and intermediates, about 300 intermediates, and the specialty chemicals are those that are made from bulk chemicals. These numbers will increase, but certainly not infinite, it is a reasonable number that you can handle. The chemical industry basically consists of the following: consists of a reactor usually at the core, whole lot of separation and recycle systems, heat exchanger networks and utilities. This is broadly the picture of the chemical industry. And after the reactor there are the separation processes, and I have to tell you something about separation process, because industrial separation process can be divided as shown in this picture roughly. You have equilibrium separation processes, which constitute about 55% of the total, and then you have 30% rate governed separation process, and you have mechanical separation process in the balance. The equilibrium separation process can be basically designed on the basis of thermodynamics itself. Thermodynamics deals with equilibrium, and many of these processes operate so close to equilibrium that you can make quantitative predictions with thermodynamics. The point is that separations are expensive. Most chemicals do not occur in the pure state in nature. So, separation processes contribute a major part, and 70% of capital investment, it is estimated, in the petroleum and the petrochemical industry is on separation equipment alone. Now, that is about the chemical industry. About thermodynamics, thermodynamics is a subject with extraordinary width of applications. You can ask questions that you may not think are significant, but as diverse as how tall can trees grow, how old is the universe, and so on. Thermodynamics has a supervisory, often intangible role in engineering. It sets the boundaries of design. Fundamentally, it will tell you what is the maximum possible thing. For example, what is the maximum work you can extract from a system, or what is the minimum work you have to put in order to produce a change of state, and so on. And in chemical engineering, the applications are in phase and reaction equilibria, in calculating separation work, and in design of equipment in near equilibrium processes. The 55% separation process are practically designed on the basis of mass balance, energy balance, and just thermodynamics. Now, the perfection of classical thermodynamics, I do not know if you have seen this book by Lewis and Randall on thermodynamics, one of the best books that is available in the market. It is an old book, it has been reprinted I think the revised edition is by Pitzer and Curl. But if you look at the preface, G.N. Lewis says, when you visit an ancient monument, you see only the perfection of the completed whole. Enter such an edifice that is still under construction, you realize that these great structures are but the result of giving to ordinary human effort a direction and a purpose. I think the point that Lewis makes particularly is that thermodynamics as a subject appears so complete, and the completion itself gives it a perfection. It's sometimes a little frustrating for the novice, because it seems as if you are drawing conclusions out of nothing. But I think it is nice to go back to the masters who gave direction and purpose to the edifice called thermodynamics and ask what did they contribute. In some sense it is nice to have a sense of history of the subject. So let me start with a few of these people. Galileo Galilei must be recognized as the person who introduced in effect the scientific spirit. He said you not only have to collect data, you have to then use your right brain to arrive at conclusions, far reaching conclusions, and then when you hypothesize, you have to also verify experimentally, because a lot of your imagination of the right brain is often wrong. Of course, Galileo did not talk about the right brain, the left brain, but in our context we can explain what he said in these terms. Isaac Newton, of course, was the one who essentially, as far as thermodynamics is concerned, introduced the concept of work and told you how work is calculated. Sadi Carnot is a rare case of an engineer contributing to fundamental science. The second law actually came before the first law, and Sadi Carnot introduced the idea of absolute temperature. Then there was Joule, who introduced the conservation of energy in a very rigorous form. I will say a few words about each of these people. And Rudolf Clausius, who introduced the word entropy. So this is, I can't get a picture of Galileo as a younger person, unfortunately, but Galileo was a father of modern science and all, effectively. Newton discovered the laws, as you can see there, of calculus, gravity, motion and optics, and then turned 26. So this was an Englishman whose contribution is well known. And then we had Carnot and Clausius, the French engineer scientist. You are moving a couple of centuries after Newton and Galileo. The Carnot was a bachelor who died young, but essentially came up with the second law. And the German physicist and mathematician Clausius was also a neologist. He had a knack of coining words that remain in use even today. So he introduced the word entropy, for example. Let me talk a little bit about their ideas. The heat to work conversion, essentially Carnot pointed out, was asymmetric, and he introduced the concept of a heat reservoir that was so large that a little addition of heat and taking a little heat away from it does not change its thermodynamic state. And he introduced the concept of a reversible heat engine. He realized that in order to produce work you have to have a cyclic operation, otherwise the amount of work produced would not be significant. And he introduced the concept of a heat engine that would work both ways. And the thermodynamic concept of absolute temperature came from Carnot again. He also talked about the efficiency of the reversible, the Carnot, now called Carnot engine, operating between two heat reservoirs at T1 and T2, and said that the efficiency must be 1 minus T2 by T1. He said no heat engine can be more efficient than the Carnot engine. The entropy definition was actually given by Clausius, although it was Carnot who pointed out that delta Q by T, while delta Q was a function of path, delta Q by T defined a quantity that was a change in a property, and he used this to define entropy as a function of state. And the conclusion was that the entropy of the universe, which is the only isolated system we really know, can never decrease. So Joule and Kelvin, these are pictures of Joule and Kelvin. Joule was characterized by dogged persistence. I will say a few words about what he did, and then talk about Lord Kelvin a bit. What Joule said, it was even before Joule, it was known that there were two ways of exchanging energy with the system and between the system and the surroundings, and it was Joule who essentially asserted that there are only two ways as far as a closed system is concerned. The interaction, energy interaction, was either an exchange of heat or exchange of work, and he did several experiments to show that this was true. He is supposed to have told the Royal Society again and again, demonstrated this in front of the Royal Society, till the members of the Royal Society were absolutely convinced. They did not want any more persuasion, but Joule insisted on doing it in several ways. But he essentially showed that heat and work are equivalent, and the internal energy is a function of state. The internal energy of the universe is a constant. Of course, the internal energy he defined as the difference between heat and work. We will give you a more precise definition as we go along, and he pointed out that the internal energy of an isolated system is a constant. Lord Kelvin was one of the greatest supporters of Joule. Lord Kelvin came from the aristocracy, whereas Joule was an ordinary citizen, and this support is very valuable. But Lord Kelvin is known to be very embarrassingly self-confident. There is a story that he wrote the tripos, and he sent one of the attendants asking him to go look up the results of the tripos, and said, find out who is second. And he supposed the attendant seems to have come back and said, Lord, you are second. So he was actually, he was very confident that he was going to be the first ranker. Somebody else had to be second. But he provided a lot of support to Joule in the Royal Society in those days. Then a little later, there were this van der Waals and van Laar. Van der Waals again from Netherlands, both of them, and van der Waals was a Nobel laureate, one of the first in the area of thermodynamics, and also a nepotist. He apparently got his son to succeed him, and he was the first one to produce an equation of state that is even now used as one of the best equations in conceptual terms. It has no conflict in any fundamental way with thermodynamics, the laws of thermodynamics. He talked about capillarity, and he also introduced the idea of corresponding states. Van Laar was a student. He was socially awkward, and but he was a great scientist, and he is the first one to have produced a classical thermodynamic theory of solutions. It's still one of the best. Then there were Boltzmann and Gibbs. Boltzmann was a moody German. He actually finally committed suicide, but his ideas were far ahead of his time and introduced kinetic theory essentially. And then there was Gibbs. Boltzmann, on the tomb of Boltzmann, this formula of S for an isolated system is given. S is equal to k log omega, where the omega is the number of microscopic states in which the macroscopic system can exist. Gibbs was one of the most remarkable people, the best of the early expositors. He also developed the statistical and mechanical principles. And he was a remarkable man. He was in Yale for many years without any payment, and subsequently he was finally recognized, before he retired, he finally recognized as one of the great scientists. And his book on elementary principles of statistical mechanics still reads beautifully, and after about 150 pages that he had written, all of this work was done in isolation, all by himself. He finally calculates the specific heat of argon, and he makes a comment that the specific heat that we predict does not agree with experiment, therefore we must consider our methods as tentative. Actually, a couple of years later, the specific heat was actually remeasured, and it was found that Gibbs's prediction was right and the old experimental data was wrong. So he is an absolutely remarkable person, and a lot of results, a lot of things you can do. Classical thermodynamics in many ways is a very complete subject, and a lot of things you think you can derive on your own, you will find in a footnote to Gibbs's notes. It can be shown that, and the result is recorded there. So basically, let me just say that classical thermodynamics is essentially two laws. It says the energy of an isolated system is a constant, and the entropy of an isolated system is ever increasing. The equivalent statement of the laws, as far as we are concerned, is that the internal energy U and the entropy S are functions of state. We know other functions of state like pressure, temperature, composition, volume, and so on, but these two were introduced because of the two laws of thermodynamics. Once these are introduced, the rest of it is practically calculus. You can derive all the results in thermodynamics through calculus. Essentially, chemical engineers are interested in two kinds of applications. One is criteria of equilibrium and the other is extreme iron work. Let me talk a little bit about closed systems, the combined form of the two laws, and we will see these in some more detail as the course unfolds, but I am trying to give you an overview here. Essentially, we are going to draw the conclusion that the change in the internal energy is less than or equal to TdS minus delta W. The convention used here for work is that for work and heat, the conventions are heat is positive if it is added to the system, work is positive if it is work done by the system. The modern convention is actually the other way around. So, in terms of delta W and delta W, the signs in this presentation and in most of the course would actually be the opposite of what is presented in most books, today's books. But it is a trivial difference because finally in terms of actually measurable quantities, the equations will be the same. So, in isentropic processes you can show that the maximum work you can get when a system changes from one state to another is actually equal to minus the change in internal energy, and minus W, which is the work done on the system. The minimum work you have to do to produce a change of state is equal to delta U. In isothermal processes we will show that this is actually equal to the free energy change delta A. For PVT systems, delta W is PdV and the equilibrium criterion becomes simply U is equal to minimum at constant S and V, because you can rearrange that first equation. You put du is equal to delta W is equal to PdV, so you get du is less than or equal to 0 when S and V are constant, which means U has to be a minimum at equilibrium. But this is a constraint of constant S and V, so if you subtract off minus Ts on from both sides, you get the result that A should be a minimum at constant T and V. Then at constant S and P, similarly H should be a minimum and G will be a minimum at constant T and P. It is clear that because temperature and pressure, temperature and volume are the pairs of variables that can be held constant through easily, you can monitor these values. So, A being a minimum and G being a minimum are the important equations. If you look at open systems, you have to subtract off flow work. So, you redefine shaft work or useful work as delta W plus what I have written there, and if you put that in, you can ask what is the minimum work you have to do in a flow process, in a steady adiabatic process, and you get the result that minus delta Ws by delta M is equal to delta H. Similarly, in steady isothermal operation it is equal to delta G. Now, this is also valid for systems with negligible hold up, and a chemical plant, for example, if you take a whole plant where raw materials enter and the products leave at ambient temperature and pressure, no matter what happens inside the plant, you can calculate simply the delta G between the product and the products and the raw materials, and this is the minimum work you have to do. Of course, the actual work will be much more, but it is remarkable that thermodynamics is able to make such predictions while not paying attention to the details. So, let me show you an example. This is an example of an undersea portable device. I have a tank 1 and tank 2. This can be used, for example, for working on the hull of ships, and this is a portable device which is carried on the back of a diver, and you can ask how much work can this do, what should be the, what you have is air in tank 1 at very high pressure which expands into tank 2, because you are talking of pressures under the sea and the pressure can be quite high, even at 10 meters it can be quite high. So, what you do is always have an evacuated tank which is much larger, into which the air expands, and in doing so it does work Ws. You can ask what is the amount of work done. So, I have given you some example. Tank 1 you start at 50 atmospheres and go, tank 2 is at 1 atmosphere at T is equal to 0, and you allow the air from tank 1 to go into tank 2. The volume of tank 1 is 5 liters, and tank 2 is 50 liters. And you can ask, when it comes to equilibrium, what will be the final pressure. You can show that the pressure is 5.43. The operation is isothermal because the whole thing occurs underwater at a particular depth and the temperature is constant effectively. So what you can do is calculate therefore the maximum work. Maximum work according to thermodynamics is delta A, and you are talking of m1, the mass of air in tank 1 having a change delta A1, that is a specific Helmholtz free energy small a, and m2 delta A2, that is the gas in tank 2, and the second part is compressed, the first part expands. So you have a net work done of 46.9 kilojoules. So if you are looking at, what we are really looking at is mixtures in chemical engineering thermodynamics, and you have to start with the basic laws for dG, for example, because the Gibbs free energy is the most important variable, because typically chemists deal with closed systems and they use A as a very important variable, the Helmholtz free energy, and chemical engineers deal mostly with flow systems. So we are looking at G as the most important variable. The Gibbs free energy dG is simply minus SdT plus VdP plus sum over mu I dNi. You are looking at it as a natural function of temperature and pressure and mole numbers, and the change in G with respect to Ni at constant Tp etc. and other mole numbers is a variable that will appear again and again. It is called partial molal property Gi bar. It is given a name, chemical potential mu I. Mu I has other definitions, but basically you can take the first equation dG equal to minus SdT plus VdP plus mu I, sum over I of mu I dNi, and because if you are looking at a process that at constant T and P, and because mu I is an intensive variable, if you look at changing G from a system with n moles to k times n moles, you actually get this result by integrating the first equation. You get G is equal to sum over Ni mu I. This is true of any partial molal property. So in particular for the chemical for the Gibbs free energy, the chemical potential is the partial molal property, and G is simply equal to sum over Ni mu I. And you can write this by differentiating this again and comparing with the first equation, you get what is called the Gibbs-Duhem equation, minus SdT plus VdP plus sum over Ni d mu I. It was Gibbs who pointed out that chemical potential is actually the natural variable for discussing thermodynamic theory, not composition. But like the composition variables, the mole fractions for example, out of n only n minus 1 are independent because there is a constraint that sum over xi is equal to 1 or sum over dxi is equal to 0. An equivalent equation can be derived for the chemical potential, and that is this equation here, because chemical potential is given by this equation from calculus, and you can use the Gibbs-Duhem equation, re-express the Gibbs-Duhem equation by substituting this for d mu I, and you get a simple result that sum over I of xi dou mu I by dou xj, the sum over all I is equal to 0 for every j equal to 1 to r minus 1. So you have a total of r minus 1 equations for r chemical potentials in any given phase. Therefore there is 1 degree of freedom. Now you can therefore guess the composition dependence of the chemical potential of one species, and then all the others are determined by the Gibbs-Duhem equation. The simplest of these solutions is called mu I is equal to mu I reference plus RTL and xi, and if it is valid all the way for the whole range of compositions, then when xi is equal to 1, mu I reference becomes the chemical potential of pure I. So as I said, the Gibbs-Duhem equation has r unknowns and r minus 1 variables and r minus 1 equations, sorry. So it has no unique solution. The central problem then is to build models for any one chemical potential. Instead of doing it for one chemical potential, you try and do it for delta G mix, because delta G mix is simply the free energy change due to mixing of components. So after mixing the Gibbs free energy is xi mu I sum over all I, and before mixing it was all pure substances, so it is xi mu I pure, and delta G minus delta G ideal is called G excess. So, if you can make a guess for Gxs, then you can calculate the chemical potentials, and in given Gxs, for example, in a binary, the chemical potential mu1 is simply delta G plus x2 times partial of delta G with respect to x1, and this is formally written as mu I pure plus RT log gamma I xi, where gamma I represents the non-ideality, and RT log gamma 1 is Gxs plus x2 delta of Gxs by delta x1. So, this way all you have to do is guess what Gxs is or delta G of mixing is. There are various models for this because you have complete freedom. Only thing is the model that you propose has to give results that agree with experiment for a large number of systems, then it stays in the literature, otherwise it is forgotten. So, the models, for example, a Van Laar model, Dolza, like these two are classical thermodynamic models, the others are all molecular models. You have various models like the Wilson, the Uniquac, the Scatchard Hildebrand, the Florey-Huggins model, and so on. So, basically what you are looking at is bounds for work. You have to calculate the change in the thermodynamic properties, either U or A, or the specific enthalpy or the specific Gibbs free energy. Particular interest in separation process is the free energy of mixing, as I pointed out already. Delta G mix is delta H mix minus T delta S mix. All of the models normally try and calculate H, delta H or delta S, and then set the other, have a default option for the other. For example, you can say delta H is 0 and I will calculate the entropy of mixing, or you can say delta S mix is the same as the delta S of ideal mixture and calculate model delta H. Delta H ideal, delta G ideal is simply RT times xi log xi. Just to give you an illustration, take work of separation. For example, you have, let us say, a distillation column in which you are separating ethyl benzene from the 3 xylenes, para, meta and ortho, and I have a certain feed, I have a certain overhead composition. In a distillation column I have a middle composition and a bottom composition. The question is how much work is required for this. Now, the minimum work that you have to put into the system is simply G of the products minus G of the feed, and in this case there are 3 product streams. So, delta G of P1 plus delta G of P2 plus delta G of P3 minus delta Gf. You can write it in terms of delta G for each stream because the pure component free energies will cancel in any case. So, delta G ideal in this case turns out to be 2.86 kilojoules per mole. If you use a regular solution model, you will learn all these models later in the course, you can show that gives you an excess free energy of minus 1.88. So, net delta G is 0.98, which is the minimum work that you have to do. It should be minus W within parenthesis, then minimum, because it is work done on the system. Now, delta H is 0.81, so you can, the enthalpy contribution is approximately 80%. This particular case that we discuss is an example of a dominant enthalpic effect. Now, if you look at work per mole, minus RT times x1 log gamma 1 x1 plus x2 log gamma 2 x2 represents delta G, and it is the minimum isothermal work to be done to separate 1 mole of a binary mixture into x1 moles of component 1 and x2 moles of component 2. Of this, minus RT ln of gamma 1 x1 is the work needed to produce 1 mole of the substance from its naturally occurring state of composition x1. Now, in a free market, the price you would expect that the price per mole be determined by the work needed to produce it, and I will give you an example of a plot. This is from Judson King, the classic book of 1970, and he plots log of the price in dollars per pound against log of the weight fraction. It should be mole fraction times the activity coefficient, but as an crude approximation you can use the weight fraction, and if you make a plot you get a remarkable straight line. The two data are from completely different sources. The one is the market price and the other is the log of the weight fraction as it occurs in nature, and this approximately calculates the work required. So, you can see that the thermodynamic work required correlates very well with the price. The slope also depends, and the slope of this will depend on several factors including the economic conditions, the wages and so on. Now you look at it is a free market, so everything falls in place. Look at some data for India that we plotted. This is 2001 data, it is old data but it still gives you a flavor. You can see that petrol is much higher, that is artificial because you have an excise duty on petrol, and you can see that urea pre-subsidy is right bang on the line. The actual price of urea is much lower in order to get the vote of the farmers, and to make it available for the farmers the government makes it available at much lower prices. Sugar again is a political decision to subsidize sugar, and so you get sugar at much lower price than the work warrants. So criteria of equilibrium, I want to say a few words about the other aspects of thermodynamics. At constant T and P, thermodynamics will tell you that G should be a minimum, and G is Ni mu I. You can write it in terms of activity coefficients, and it is either the activity coefficient is gamma I xi if it is a liquid mixture, it is equal to P yi times Vi if it is a gaseous mixture. It is different ways of expressing the non-ideality, and by asking that delta G be equal to 0 for equilibrium, you actually come to the conclusion that RTL and K, where K is the equilibrium constant, is equal to minus delta G reference. The reference state should be chosen judiciously, and finally for phase equilibrium you can show that the chemical potentials in two phases of the same substance should be equal at equilibrium. And let us, for example, let us take a very simple example. Almost all the ores appear as sulfides or oxides. In the case of zinc, it is zinc sulfide. You roast it on oxygen, what do you expect to get? You can show that you expect essentially zinc oxide. The possible reactions are listed there. Zinc sulfide plus oxygen will give you zinc oxide plus sulfur dioxide, and the delta G0, the free energy change in standard state, is minus 280. Look at all the others: sulfur dioxide going to sulfur trioxide, zinc plus sulfur trioxide giving you zinc sulfate, and zinc oxide giving you zinc plus oxygen. All of these are positive, and you can say only the first reaction needs to be considered, the product will be zinc oxide. So thermodynamics can tell you right away what to expect in terms of product. You can of course quantitatively calculate them. Then you take a couple of reactions, for example these reactions where carbon dioxide plus hydrogen gives you carbon monoxide plus water, and then CO plus hydrogen can give you carbon deposition. Now you ask, if you do not, this carbon can deposit on the catalyst and choke and make the catalyst ineffective, and so you want to know what should be the pressure at which you should operate, or what should be the range of pressures over which you should operate. This example is at T is equal to 1000 degrees. Normally the temperature is chosen on the basis of kinetic considerations, not on the basis of thermodynamic consideration, and some data is available. You can do this calculation quite quickly and show that for pressures below 2.5 atmospheres you will have no carbon deposition. These are very powerful conclusions from where we started. So let me summarize the results. The thermodynamic theory is so beautiful and so complete that it sort of gives you results of the same form in many contexts. If chi is a characteristic intensive property at equilibrium, right through thermodynamics will tell you how to calculate chi from one of the criteria that we already discussed. It will also tell you that the change of log chi with respect to T is given by an equation that says minus characteristic enthalpy change by RT squared. Similarly, the change of log chi with respect to P will give you a characteristic volume change by RT, and the maximum minimum work will be change in the appropriate energy function. So this is a summary of results that you get in thermodynamics. They are always of the same form, and let me now pause and give you a molecular picture. For example, in the case of one example, as I said, classical thermodynamics does not depend upon the molecular structure of matter. If you look at the picture from a molecular structure, however, it is quite insightful. If you look at dissolution of salt in water, when the salt molecules are added to water, because of the high dielectric constant, the ionic forces are much weaker in water and the salt ions can separate. So, effectively the salt has more states in which it can exist, and therefore its entropy actually increases. Molecular theory tells you that the entropy depends on the number of possible states in which a system can exist, and this entropy of the salt increases while the entropy of water decreases because of the presence of salt molecules. Now, the increase of entropy of the salt is much greater normally than the decrease of entropy of water, and dissolution is therefore spontaneous because the resulting entropy change is a driving force. The energy absorbed to break the bonds in the crystal, in order to do this at a molecular level you have to break the bonds in the crystal, and this energy we will call this E A, and energy released when ion water bonds are formed, let us call it ER. Now, the comparison of EA and ER will determine whether the dissolution is going to be accompanied by a temperature change. For example, in the case of NaCl, EA is approximately equal to ER and the dissolution is more or less isothermal. But if you take ammonium nitrate, EA is so much greater than ER that the resulting decrease in temperature is so significant, it is often used as an instant cold pack. So, what molecular theory does for you is give you a mechanistic handle, and therefore most of the theories in thermodynamics for calculating property changes come from molecular theory. The classical thermodynamic theories are very few. As I said, I mentioned Van Laar and Dolzalek for calculating delta G, and they both are, came up with classical theories. We will discuss them in the course. So, in summary, the whole purpose of this course is to help you calculate thermodynamic properties and therefore calculate changes in thermodynamic properties. It is these changes that are going to be very important as far as the chemical industry is concerned, and because your prediction of both equilibrium and the maximum work that you can get from a system as well as the minimum work you need to put into a system are both determined by these changes. So, I think that is the summary of the course. You can see that there is a relevance of thermodynamics directly to the industry. That plot that I showed you of especially the agreement between the correlation between the price in the marketplace and the mole fraction or the weight fraction of the substance as it occurs in nature is particularly revealing. So, this is sort of a motivation for studying the subject, but you must realize that when the masters set up the subject, it was not at all clear that there were going to be such far reaching applications. It's a remarkable fact that by pursuing the laws and pushing the frontiers, you can get results of great significance for the modern chemical industry as well.